Hi everyone, and thanks Camilo for the introduction and for inviting me. So it's my second visit to IAS. The first one was a long time ago, so I'm really happy to be here. As Camilo said, I'm a computer scientist. I do complexity theory and quantum information theory. Where I'm going to tell you a little bit about some problems in operator algebras that together with my co-authors, so I put the names of the co-authors here, we resolved a year or two ago. So I was, I know there's mathematicians in the audience, there's computer scientists in the audience. I was warned there's even physicists in the audience. So I try to keep it as elementary and slow as I can. Feel free to interrupt me if you have questions, especially clarification questions on notation and things like that. So what I want to do in the 3 lectures is that I want to start by introducing the problems that we'll be talking about. So this is Kahn's embedding problem, which is a problem that was posed by Kahn in the 1970s when he was working on the classification of Neumann algebras. I also talk about Tsirelson's problem, which is a problem that emerged from very different sources. It's a problem in, Tsirelson is a mathematical physicist. It's a problem in the foundations of quantum mechanics, how you model locality in quantum mechanics. But it turned out to be an equivalent problem to Kahn's embedding. So what's maybe a little bit special and interesting about the lectures is that we're going to resolve both problems using an argument from computability theory, so in the sense of Turing. The core of the argument is that we're going to show that an explicit function that I'll define in this talk is uncomputable, cannot be computed by any algorithmic means. And this will imply a negative answer to these problems. So that's what I want to do in the first lecture. I just want to set the stage, give you, so there's many different reformulations of these problems. I'll just give a couple that are as concrete as possible. And I'll explain how we can provide a negative answer to the problems by using computability. So I'll make this connection today. And in the next 2 lectures on Wednesday and Friday, I'll give some of the arguments that go into the proof of the uncomputability, so the uncomputability argument. And these arguments will come from many different areas. So we'll be using a little bit of quantum information theory. That's the theory of nonlocal games or Bell inequalities, if there's any quantum physicists in the audience. That's one of the ingredients. Then the other 2 ingredients, they're complexity theory, of course, the theory of interactive proofs, PCP theorem from complexity theory. We'll make important use of that. And the last ingredient is maybe a connection with group theory and the area known as stability. So there'll be some stability questions, group theory that'll show up in the last lecture on Friday. So that's my outline. So today I just want to define the problems and make the connections. So even though Kahn's embedding problem is a problem about von Neumann algebras, I prefer not to talk about von Neumann algebras. So I'm not even going to define them. I will define what's a C-star algebra, and for the non-mathematicians, you can just think about matrix algebra. So I'll say this, but this is a definition that we use throughout. So I'll give it. So a tracial C-star algebra is a pair of an algebra A and a linear function on A such that, so A is a C-star algebra. C-star algebra, so if what it means just for us, so I'll just say that it's a norm closed, the operator norm closed, star closed, so star is the adjoint subalgebra of bounded operators on a separable Hilbert space. And tau is a trace on A, which just means that so it's a function from A to C such that it's normalized, so the identity is mapped to 1. And it's positive, so tau of A star is positive for every A 0. In particular, it has this implies that it has a cyclicity property. Okay, so that's the definition. Just have the definition on the board. But if you don't really care, for most of the talk, I'll only be concerned with actually finite dimensional algebra. So a typical example would be that A is finite dimensional matrices of complex numbers, and the trace I'll write it as tau d. This is notation that we use. It would be the normalized, dimension normalized matrix trace. Okay, that's one example. You get another large class of examples, which is kind of relevant by using groups. So you can take, I'll try to make this fit here. Another class of examples is you can take gamma to be a countable group. Then you can form Hilbert space L2 of gamma. This is just a separable Hilbert space that has a basis indexed by orthonormal basis indexed by the elements of gamma. And then you can consider the left regular representation of gamma on this space, which just acts by shift. So any group element G permutes the orthonormal basis of L2 of gamma according to the group multiplication. So these define kind of permutation matrices on that space, and you consider the algebra generated by all these permutation matrices. This is an infinite dimensional C-star algebra, and the trace is just given by you look at okay, so E is the identity of the group. This is the basis element of L2 of gamma that's associated with the identity element of the group, and this is just the scalar product. So this is like the top left corner of the A matrix. Okay, so this is a trace of this C-star algebra. Okay, just to say that there's this, just to give you an infinite dimensional example. Okay, all right. So let me now state Kahn's embedding problem. I'll actually give a formulation that's due to Kirchberg. So Kahn's embedding problem was posed in the 70s by Kahn, but it's kind of like an offhand remark in some paper about classifying von Neumann algebras. And one of the reasons that it became a prominent problem in operator algebras is the work of Kirchberg, who gave multiple reformulations in terms of questions about tensor products, different ways that you can norm the tensor product of C-star algebras. And I'm not going to talk about that, but I'll give you a very concrete formulation now, which kind of comes out of the work of Kirchberg. What I'll say appears in a paper by Dikema and Yushchenko from 2009. So here's the conjecture. I call it conjecture K for Kirchberg. So the conjecture says that for every C-star algebra, so of this form, then for every integers n and k, these are integers, and for every approximation parameter epsilon, so whenever you take n unitary elements in A, so for every u1, un, these are unitaries, so this means unitaries on this algebra A, and they have order k. So this is kind of like just a simplification. They're not completely wide unitaries. We control the spectrum. For unitaries of order k, there exists finite dimensional approximations to these unitaries in the following somewhat weak sense. So there exists some integer d and u1, un in. So now these are unitaries on CD. They're also of order k. Such that if I look at the order 2 moments, but I think of these as correlations, kind of like inner products between these matrices. So I look at all ui, uj, let's have alpha and beta. I look at this and I compare it to the order 2 moments that are given by the small finite dimensional unitaries, alpha, beta. Then this is less than epsilon for every I and j between 1 and n, and for every alpha and beta between 1 and k. Okay, because they have order k.
But to be clear, Kahn didn't conjecture.
Or right, so I wrote it as a conjecture because so Kirchberg did conjecture something like this, like the Queb conjecture, but yeah, thanks. So Kahn's just posed it as a problem, I guess. So that's why in the okay, you can't see it, but okay, so
Could you say what order k means?
Can I say what? Sorry.
What order?
Yes, of course. So it means that ui to the k is equal to 1. So it just means that so the eigenvalues are k.
And this, you don't require some bound on D in terms of.
No, so the conjecture only states that there should exist a finite D, and this D is allowed to depend on everything that came before, so including the algebra, the unitaries, the epsilon, everything. So let me give you another formulation that maybe I'll do it here, that does away even with the C-star algebra and only talks about groups and representations of groups. I'm also introducing this because I want to connect this problem with the question of hyperlinearity or sophicity of groups that is maybe more well known. The next formulation that I give, I forgot to say this, I took it from some lecture notes that De La Salle prepared for a Bourbaki seminar that was given about this work like a month or two ago. And they're very good notes, and I took inspiration from them to prepare the talk. For me, I think they helped me try to find a way to say things to mathematicians, which I hope I manage. Unfortunately, these lecture notes are in French. So if you read French, I highly recommend them. If you don't, you can try to use Google Translate. I also have some less good, but still kind of like explanatory notes that I wrote for a presentation at the ICM last summer. So you can also search for that. Okay, so here's a reformulation of what I just wrote. So reformulation. So sorry, I need just a couple of definitions. So if gamma is a countable group, definition, a character is a map from the group to the complex numbers such that it's normalized. So phi is 1, phi is invariant under conjugation. And it's positive, so this is the main condition, phi positive. What it means that it's positive is that the matrix, the finite matrix phi of gamma inverse gamma j, so this matrix should be P as D if for every n and for every element of the group. Okay, so you take any number of finite elements of the group, you make this matrix, which is square of size, the number of elements you chose, and it should be PSD, okay, for any number of finite elements. So this is the definition of a character, and let me give you the reformulation now. The reformulation, okay, sorry, some examples. Okay, so in finite dimensions, you can take phi of gamma to be tau d. Remember that this is the dimension normalized trace of phi of gamma, where phi is a unitary Okay, so you can take unitary representations of your group in finite dimensions, and you can take traces of that, and that gives you characters. But there's other examples. For example, you can take phi to be the indicator function of a normal subgroup. So n normal subgroup. Okay, so that's another example which I'll use in a second. Okay, so let's take F2, be the free group on two generators. Okay, this is just a group generated by A and B. So you have A and B, and you can multiply them in any way you want, and there's no cancellation at all. And the conjecture, which is equivalent to K over there, conjecture is that every character of F2 is pointwise limit of finite dimensional characters. So depending where you come from, this could be more or less concrete. It's more concrete because it doesn't involve C-star algebras. It just involves a very specific group and something about functions on the group being approximated by finite dimensional versions of these functions.
Sorry, in this definition, you're requiring phi of G is phi of G inverse conjugate.
Here?
Yeah, that is a PSD includes that it's self-adjoint.
Yeah, so it'll come, yes. PSD means self-adjoint and all the eigenvalues are non-negative. So if you know a little bit about these things, if you know this is a very strong condition, and any positive map actually must come from a map that you can extract. Yeah. Anyways, okay, I cannot explain, but it's not, if you know, it's not hard to show that this is equivalent to this.
This fact that this conjecture, I mean, one direction is obvious, the other direction that you can get it from the group, is that obvious? That every Hilbert space case can be realized this way. You're saying they're equivalent?
Yeah, they're equivalent. I don't think it's hard. I found it in the book by Brown and Ozawa. So this is not my real, so but it's like maybe a couple pages.
I mean, because my understanding is that some version of your counterexample does not exist at the level of C-star group algebras, right?
Right. So here, so we're not quite there. So I'm going to take this right now. So if I formulate it here for every character, then we get these two conjectures are equivalent. Now I could specialize to characters of this form, characters that are the indicator function over a normal subgroup. If we do that, so if we specialize to characters phi of the form the indicator of a normal subgroup, then this is a weaker conjecture because we're only asking for those characters to be pointwise limits of n-dimensional characters. This is the conjecture that every group or every countable group is the same thing. So let's say that every countable group is hyperlinear. This is again something not so hard to see, but I won't show it because I don't want to define hyperlinearity on the board, but I just say it in words. So if you don't know what it means for a group to be hyperlinear, listen to me. So you take a countable group. Actually, it's easier to state for a finitely presented group. So you have generators and relations, and this group is hyperlinear if and only if every finite subset of the group can be well approximated by finite dimensional matrices. Okay, so it says that finite subsets of the group approximately embed into finite dimensional unitary matrices. And so this is equivalent to that. If you further specialize to here requiring that it's a limit of finite dimensional characters that are of the form like this, but they map into permutation matrices now, as opposed to unitaries. Then you get an intermediate conjecture, so it's stronger than hyperlinearity, but weaker than K, which is the Romov's group sophicity conjecture, the conjecture that every countable group is. So as Peter pointed out, what we're going to refute is the strongest version, is this version. The conjecture of every group being hyperlinear or sophic, these two conjectures are still open. This is because we're going to construct an explicit counterexample to the conjecture. So a specific character that is, we'll be able to show is not a pointwise limit, but this character will not have that. That's all I wanted to say about Kahn's embedding problem. And I think if you're not an expert, the way I think about it is that it's a problem about finite dimensional approximation. So you're taking certain kinds of objects. These objects could be countable groups, or it could be von Neumann algebras or C-star algebras. Of course, there's many subtleties, and you have to be very careful when you talk about for the question to be possible and not trivial. But still, there are questions about finite. This is a question about finite dimensional approximations, right? You're asking if every kind of correlation that you can create between infinite dimensional unitary matrices can be approximated. Questions? I'm going to let me tell you what's next. Next, I want to talk about Tsirelson's problem, which comes from a very different area, but you'll be able to see in the end poses a very related question. I mean, in fact, they're equivalent. This will be less obvious, but the fact that they're related. Okay, so I want to keep this for later, but we would erase this there. So Tsirelson's problem is a problem in physics, in quantum physics. It's a problem about the appropriate way to model mathematically a certain kind of experiment. So let me tell you about the kind of experiments that we're considering. So we're looking at this kind of scenario. So there's two different physical systems, A and B, and these systems are isolated. So everything I say is non-relativistic, but so you imagine that they're isolated in space-time. So there's no exchange of information, no communication that's possible between them, but they're physical systems. And at each system arrives an input, X here and Y here. So they're chosen in some finite set of possibilities. So there's n possible choices for X and possible choices for Y. Think of this as an input or as a measurement setting. Later we'll think of them as questions, but it's the label of some observation that you make on system A. And you make the observation and outcomes an outcome A and B. And the outcomes, I label them using also integers between 1 and k. Okay. So you can think of n and k as small, like n could be 10, k could be 5, could even be 2. Okay, and you want to model what can happen in that kind of situation. So the main object that we look at is this. So if you do the experiment and collect statistics for every possible pair of inputs, you put these inputs, you repeat it many times, you're going to collect outputs A and B, and you'll be able to estimate the probability that A and B are obtained, given that the inputs are X and Y. And the mathematical model in question is, what is the set of probability distributions or families of probability distributions of that form that can be generated in a physical experiment like this, depending on the physical theory that you use. So if you are not a physicist, you haven't thought about this before, maybe the most natural reaction is to say, well, okay, you told us that these two systems are isolated, so whatever they generate, this must obey some kind of a product distribution. This should have the form, there's going to be some distribution of what happens at system A, and this will be this, and then there's going to be some distribution at system B, and so we'll only be considering distributions of that form. In fact, to make the problem nicer, and it's also reasonable, we can imagine that systems A and B are in a state that's correlated. That's correlated according to some past history. So I'll write this as lambda. Lambda is just some, it's called a hidden variable. In physics, which is some variable that can be used to describe both the state of A and the state of B. So maybe before these inputs were generated, A and B were in the same place, and they share some information that was generated probabilistically. So this means that we can extend a little bit the kind of distributions that might be generated in the experiment by having a dependency on lambda here, and then we average over lambda, and there's some measure of lambda, which doesn't really matter what it is. So I'm going to introduce notation for the class of distributions that have this form. I'll write it C class. It's the classical set. There's only two parameters here, n and k, and then this is the set of all distributions of this form. Okay. This is a subset of. So I'm sorry, I didn't. What I consider is the tuple. So this is each of these is a number, and I have n squared times k squared numbers. So this is a subset of 0, 1, n squared k squared. Okay. And I can try to study that subset, and I'll maybe draw a picture here. So remember that n and k are small, so potentially I could draw it on the board, but they're not that small. So I can take the whole board for all possibilities, 0, 1, n squared, k squared. But of course, not all of them are possible. First of all, we're like in lower dimensional, because for every x and y, I need to have a distribution. So the sum over all A and B should be 1. I mean, that's obvious for it to be a probability. So I need to cut this. But ignoring that, what we have here is a polytope. So it's okay, it's a polytope. It has a certain number of extreme points. The extreme points are the deterministic product functions. So just PA of so just when PA and PB are indicators, like each x is mapped to a single A. And then other than that, it's a convex set. It's like this, right? So every point here is a vector of n squared k squared coordinates, and it tells me all these probabilities. Okay.
Is it codimension 0?
Yeah. If I write it this way, yeah, because of the normalization conditions. So just ignore that for the sake of the picture. No, I'm sorry. It has positive codimension. So it's you wouldn't see it. So, but I just sorry. It satisfies linear. It satisfies linear equations. Like if I fix x and y and I sum over all a and b, I always get 1. So it's in a specific affine subset. Is that okay? Or maybe is the like definition okay? Or?
Just to ask about lambda again.
Yeah.
So before the experiment starts, there is some lambda that both share, and then you perform the experiment. But then when you said that these statistics are collected, so each time you re-perform the experiment,
I imagine that I can do it with this.
a new lambda.
Yes. So this is why the object that I'm estimating is this. It's not the individual ones. That's the model. So that's the model in classical mechanics. Tsirelson's work was prompted by the fact that since the 30s or even earlier, people had discovered that if you model the experiment using quantum mechanics, you can write down distributions that can be generated locally, but they're not here. They're like here. And so. And furthermore, did experiments to see a distribution that lies outside.
What sort of an object is that? I'm sorry.
So this is
Obviously
it's not important, so you shouldn't worry about it because I'm not going to talk about it. But it's you could imagine that it's just a discrete variable in some discrete set. So it's lambda in some finite omega, and I would range over all possible finite omegas to write the definition. If I want it to be nicely convex, I need to allow measures here that have real coefficients. But it's not really important. But you're not going to talk about it.
You can go the other way around, right? Just define it as the convex hull.
I could define it as a convex hull and then forget about it. Right. We could just have taken product distributions, which are the extreme points, and taken the convex hull. Yeah. Okay, so to tell you how the experiment is modeled or can be modeled in quantum mechanics, I need just one definition. It's the definition of a measurement in quantum mechanics. So I've only used projective measurements. So PVM, this stands for projective valued measure in or on H. H is a separable space. Is just a collection, let's say PI, such that each PI is a projection, and the sum of the PIs is the identity of PI. So it's just a partition of identity using projections. Sorry.
Projection is just PI for this PI, or
yeah, and it's Hermitian. So we're talking about projection.
PIs are not required to commute with each other.
Well, they are by virtue of this. So this forces them to be orthogonal to each other. So implicitly, yeah. But in general, there's a more general notion of measurement, which doesn't require them to be projections, just requires them to be positive, and no, they're not required. Okay, so using this notion, I'm going to define two other sets of distributions that were introduced by Tsirelson. So the first one is called the quantum set. I'll write it with a star, C star, and so this is the set of all. So same kind of experiment as before. So I'm trying to describe distributions of that form, except now the class of distributions that I consider are distributions that take this form. So they take this form, and I'll explain the object in just a second. Okay, so we have, I range over, okay, so it's things that take this form, ranging over all Hilbert spaces. So I can choose Hilbert space of finite or infinite dimensions. Psi is a vector. In H, it's normalized. The ket there is like the Dirac notation for quantum mechanics. If you don't like kets, you can ignore it. It's just, this is just a vector, and this is the adjoint vector. And Px, A, and Q by B, these are PVM of H.
Psi to be H center, right? So
Yeah, sorry, thank you. Yeah. Okay, so this is another set. It's convex. It's not completely obvious to see that it's convex, but you can see it by taking direct sums of H and of everything involved. It's not hard to see that it contains the set above it by restricting to P's and Q's that are diagonal everyone diagonal in the same basis. You can recover on the previous set. And so I'll draw it here. It's a bit bigger. So it's actually not completely obvious that it's bigger. This is work in quantum mechanics, notably the work of John Bell in the 60s and others, to find points here and prove that these points are in this set and prove that the points are not in that set. I mean, this is really the work you have to do it. But there's very explicit points even for n and k equals 2, both of them that show this.
Is the small region dimension 0 and the bigger region?
Okay, that I don't know. My guess would be yes, and it's probably known, but I'm not sure. Sorry? It's not. So this is, you'd have to show that, but it's not a polytope. It has all kinds of, if you're interested in sets, it has all kinds of, so it does have some flat borders, it does have some extreme points, and then it has all kinds of like curved things. We'll show actually an outcome of the lectures. It's it's convex set in finite dimension. N and K are like 10 each, but it's very complicated convex set. Okay, so that's one definition, and then there's another one which is slightly more general. So C, and I'll write it as C infinity, N and K. It's almost the same, but we're going to replace the condition that P's and Q's associated with A and B act on different Hilbert spaces. Here, P acts on this H and Q acts on that H, with the condition that they can act on the same H, but they must commute. All P's and Q's must commute. So I'll write this psi A Q Y B psi. So it's not a typo. There's no tensor product here. There's just a product, and then all the conditions are basically the same, except that I add the condition that all these PXA, QY, B must pairwise commute. So for every XA, Y, B, X, Y.
But now psi is in H and not in F.
Now psi is in H, right? I didn't write it, but yeah, there's just a, okay, let me write it. Let me just check. There's no tensor product here. Okay, so some observations that that Tsirelson made are that this is a subset of this. This is pretty clear just by relabeling. You call H here the tensor product of the two H's, and P here P tensor identity, and then of course the commute. Okay, so this inclusion is clear. It's also not hard that if you restrict in both cases the Hilbert spaces to be finite dimensional, then the two sets are equal. If you have two families of operators that that pairwise commute like this, and they act on the same finite dimensional Hilbert space, then you can split the Hilbert space as a direct sum of tensor products. So you get equality. And Tsirelson in his work assumed that in fact the equality extended to all Hilbert spaces, and went on to work with this definition because it gives you a little bit more control, thanks to the fact that you have a tensor product. Like 2 decades later, computer scientists actually working on related problems were not able to show the equivalence of the assets, and then Tsirelson realized that in fact he cannot prove that the two sets are equal. And so this became Tsirelson's problem. So I can write the other set like this. And I'll write it. Tsirelson problem is the following problem is these are just closures in topological closures in this set for every so the question on the foundations of quantum mechanics, it's it's really a question about foundations. I don't think it has like practical implications, but it's kind of an important question in the sense that these experiments you want to do them and study them all the time, to study the non-local aspects of quantum mechanics, and you need to be able to say what's the class of distributions that you can generate. Is it that class or is it that class? If the two are the same, then fine, but if the two are different, then you have to make choices. Kind of a strange, strange choice to be making. Okay, but other than that, I think the question was posed, and then it's not like it was that relevant until in 2010 or something, due to the work of Fritz and Navasquez, Junger, Perez Garcia. They are mathematical physicists, and also Ozawa, who works in operator algebras. Combined work of these people showed that this is equivalent to these two problems are equivalent. Maybe I formulated them a little bit strange. So here I formulated it clearly as a conjecture. Okay, I should remove the is just to make it clear. So this is a conjecture. There's one implication that's easier than the other, so that K implies TP is not hard, and the converse is a little bit harder, but it's not, especially using that formulation, it's not, there's nothing that deep there. All right. Quick questions so far? Now we have like 20 minutes, and I want to make the connection to. So our goal is going to be to refute, in fact, a version of TP that I'm going to write on the board soon. Where our goal is going to refute this, and in the next 20 minutes, I want to explain what's our proof strategy going to be. Let me first write on the board, and I'll just be a bit lazy and reuse this if it's okay. Like a slightly simpler looking version, but that's in fact equivalent. It's called the synchronous Tsirelson's problem, and for people who work on that. So I'll change the definitions here. Instead, I'm going to replace this by some finite dimensional thing. So I'll just write here tau d. And all the rest is the same except that H is CD. So D is an integer and there's no psi, a PVM on CD. Okay, so this is what you get if you specialize the previous definition to finite D, and you specialize to a specific state. It's known as maximally entangled state in quantum information. It doesn't matter. Then you can you get this. So you actually get a smaller set by doing these specializations, but still I'll do the same here, and the conjecture will be equivalent. Okay. So this is just finite dimensional.
In your, and we haven't seen your construction, whatever it is, but you will be making a sequence of finite dimensional spaces with these with various parameters that are forced by the K conjecture, which fail, right? And that's explicit in there. Your counterexample.
Yeah. Is it
Something
explicit?
you can just, I guess I'll wait till Friday.
No, you can wait until the end of the lecture. So,
Okay.
and I'll be able to answer the question, not show you the example, but I'll be able to answer the question a little bit more when I say a little bit more about what actually we're going to show. So just in 10 minutes. Let me do something similar here. I'll just again I'll get rid of this and right here just a trace. And now there's going to be so here I range over all D, so D is like anything, and here I'm going to range over all tritial C star algebras, A tau is algebra, and these P and Q are PVMs on A, so just partitions of identity and the commutation condition. We don't need a commutation condition. We need a commutation condition. No, I don't need this condition. Okay. So it's a bit simpler. Now, if I formulate Tsirelson's problem as the equality between the closures of these two sets, then it's much easier to see that it's equivalent to this. The only kind of difference is that here I'm talking about partitions of identity or projections, and here about unitaries of order K, but by Fourier transform, these are the same thing. So any unitary of order K, I can decompose, I can do the spectral, apply the spectral theorem to it, and I get K projections, the spectral projections that sum to identity. So they're really the two.
You didn't change the name, you still call it C star.
Yes, I know.
It's not exactly.
No, it's not. Does it bother you? I could change the name.
Yeah.
Just to make sure.
Okay, let's call it Q. No, I said it, but I didn't write it. So you're right. So they're not the same sets.
But they have, if you take the closure, then they're the same.
No.
Also no.
No, they're not the same. The reason they're not the same, so Q star is not the same as C star. The reason is that here I specialized the state that was called psi before to a specific one. This is the matrix space. It corresponds to the maximum entangled state. I chose a specific state, and it gives a smaller set. The set is strictly smaller, but from the point of view of this question, the questions are equivalent. So this TP, as I wrote it there, or TP with Qs, the two questions are equivalent. The sets are not the same, but the questions are equivalent. One is true if and only if the other is true. And I didn't make my life easier or harder. I mean, I restricted both of them. So. Okay. Okay, so let me announce the proof strategy now. So our goal is to negate the statement that I just erased. So anyways, we want to show that the blue set and the yellow set are distinct. These sets are convex sets. So how do you separate convex set? You find a linear functional that separates them. Okay, so this is what we want to do. So some definitions, just one definition. Given linear functional, so I'll call it lambda. So this lambda is lambda x, y, a, b. And I think of it as a linear functional on the space there. So let me just, I'll just allow complex coefficients for the sake of it, but it actually doesn't matter. So it's, okay, so it's just, they're just coefficients, but these, I think of it as a linear function of that set. And then I'm going to consider two optimization functions associated with that linear function. What's the largest value that it takes on the blue set, and what's the largest value that it takes on the yellow set? So I will define them omega star of lambda. This will be the supremum over all, let's say, p. Okay, let me just write x in q star of lambda of x. And omega infinity of lambda will be the supremum over all x in q infinity of x. Okay. So because the blue set is included in the yellow set, this is always, this inequality always holds. And my goal is to show that there exists a lambda such that the inequality is strict. Once I've done that, I'm done. Okay. So I think I can erase, okay, I can erase this. So I can kind of answer your question, or at least partially. What we're constructing is not directly a point that's in the yellow set, but in the blue set, but it's, what's explicit is the lambda. And the way it's going to be constructed is by first constructing infinite families of lambda, where the n and k grow, but ultimately these infinite families will be packaged into a single lambda that has some finite n and k, like they'll be big with a billion or maybe bigger, but some finite things, and that would be. Okay, except that eventually this lambda will be explicit, but at first we're going to construct it in a slightly indirect way. We're going to show that a lambda such that there's strict inequality must exist using a computability argument. Okay, so now is when computability is going to enter the picture, and I want to explain that for the last 10 minutes. Okay, so the key observation is as follows. The key observation is that if two sets are equal, so if this holds, then there's a certain function. The function is a function that takes as input integer n, integer k, and lambda, which is just the coefficients. And I imagine that all these things are finitely represented. So n is an integer, k is an integer. Lambda could be complex coefficients, but let's just imagine that they're actually rational coefficients. So it takes n lambda, and this returns omega star of lambda, then is computable. Okay. So I'm going to prove this, and today, and then in the next lectures, we'll try to show that this function is not a computable function. By reducing a well-known uncomputable problem, the Turing's halting problem, to that. So we're going to show, but I'll explain that next time, that to Turing machines, we can associate any Turing machine, we can associate an n, a k, and a lambda, such that if the Turing machine halts, this is 1, and if it doesn't halt, it's small, it's less than half. And because the halting problem is uncomputable or undecidable, it will show that this function is uncomputable.
There's no complexity at all. Just
it may come in. So this is you don't count computability as complexity, or no? Okay. So actually this is no, this is an interesting question. So okay, you could even try to get rid of computability. Who needs computability?
we like.
But, okay. But unfortunately, complexity is going to enter the picture, meaning like more fine-grained notions of complexity, including like polynomial time and things like this,
Yes.
are going to enter the argument of showing that this function is uncomputable. And I don't know how to not do those.
Without that. Okay.
If you allow me to quote Michael de la Salle, so he's an operator algebra person who's been studying the work and trying to get rid of complexity theory, like when people, he feels that come on, this is a problem in algebras or group theory. There's no complexity. But he did manage, and ultimately became convinced that it made sense that you needed finite grade complexity. So that's just one data point. Okay, so anyway, so let me prove the key observation. So proof. It's kind of a good exercise in understanding the problem. Yeah.
Could you just remind the notion of computability? If
It's Turing computability. So it means that a function like this is computable. So is Turing machine okay? So a Turing machine is formalization of an algorithm. It's just a finite set of rules that says what you should do. So a function like this is computable if and only if there exists a Turing machine that takes as input this, and also you would give it a finite precision parameter, epsilon, and for every nk, lambda, and epsilon, it should in finite time return in its output a number that's equal to that plus minus epsilon. And it should, for every epsilon, it should take finite time, but the time that it takes as a function of nk, lambda, epsilon can be anything, but it needs to stop. It always needs to.
That's what I mean by complexity. We're not, but you're going to use arguments from the running times and
yeah, so we'll have to be more fine-grained in terms of
that's kind of interesting.
but not today. So later, maybe a little bit next time. So let me show you how you see this, because it's like a small exercise in understanding the sets. I'm going to give two algorithms. The first algorithm, so algorithm A. Like this algorithm A. So it's given as input n, k, and lambda, and what it does is that it returns the sequence of numbers, rational numbers, alpha 1 smaller than alpha 2, smaller than alpha d, smaller than etc., such that this sequence converges the supremum of the function lambda on this set here. So I claim that such an algorithm exists. Okay, what this algorithm does is that it computes an increasing and non-decreasing sequence that converges to the optimum of the function on the blue set. And the way it does that, you can imagine many ways of doing it, but from the definition, this set is just all things like this that can be realized on finite dimensional matrix algebras. So what I'm going to do is I'm going to take alpha d is going to be defined as the supremum of lambda on some 1 over d, I'm being a bit imprecise here, 1 over d net in CD. Okay, so you fix d to be some d, you go over all possible d's, then you take some net over all possible projections in CD, and you range over that net, and you see how best you can do, and you call that alpha d. And then as you let d increase and the fineness of your net decrease, you get the sequence that by definition converges to the supremum over this. Okay, so this is the existence of algorithm A is straightforward. Algorithm B is a little bit more subtle, so I won't give the details, but I claim that there exists an algorithm B that, given the same input, given n, d, and lambda, it returns, nk, nk and lambda, it returns now a non-increasing sequence, so beta 1 greater than beta d greater than etc., that eventually converges to the infinity. So I claim that such a thing exists. How do you see that? It's a little bit more subtle. So the way you'll do it is that you define this as the supremum of lambda of x, but now not x in q infinity, which would give you this directly, but some outer approximation of it. So I'll write it maybe qd of nk. This is a set that contains q infinity of nk, but in general it's going to be bigger. Maybe in the interest of time, I won't give you the definition, but you kind of relax. So you say, okay, you can use the definition based on characters that I gave you before. You don't try to iterate over all p's and q's, but instead you iterate over all functions of P and Q, like just what these values are. And you have to impose this positive positivity constraint, but you impose it only for bigger and bigger finite sets. So it's, I want to skip that. And it's not, it's easy. And just believe me that such an algorithm exists. You can construct nice looking outer approximations of Q infinity that converge to.
I'm confused. If two numbers are equal, how does this terminate? If they're not equal, it will terminate.
Okay, so how does that terminate? I mean, you're just maybe one step ahead of me. So right now I just claimed that two algorithms exist. These algorithms don't terminate, but if I give myself, okay, maybe I'll draw a picture to explain the end of the argument. So it's like this. So we have like this, and then I fix nk and lambda. So the omega star is lambda is here. The infinity of lambda is here. Maybe they're equal. And I've designed two algorithms. The first one, it goes this way, and it constructs value alpha 1, alpha d, that go to there. And the second one, it constructs values beta 1, beta d, that go this way. And the guarantee I have is that if I give myself any approximation epsilon, so I give myself some epsilon here, it's guaranteed that in finite time, algorithm A will return a value that's in that interval. But I don't know how much time. In particular, I don't necessarily know when I'm there if I don't know this. I just know I'll be there eventually. But now suppose that these two values were equal. So if these two values are equal, then I can run algorithm A and algorithm D in parallel. I just run them like next to each other, one step one step the other. And I look at these values, and if these two are equal, and this goes to that, and that goes to that, at some point they'll be close to each other, right? So there will exist some D prime such that, or let's say D epsilon such that alpha D minus beta D is less than epsilon. And at that point, I can return whichever one of them, or maybe the average, as an approximation for as a valid approximation for this. So consequence is that if TP holds, so if these two values are equal, then I can run the two algorithms in this way, and I can compute this common value is computable. If it's not computable, it must be because there's a gap between the two. Is that okay? I mean, that's the end of the proof of the observation.
Yes, I'm sort of uncomfortable with the equal case.
Okay, so I should take the equal case because the only thing I'm trying to do right now is prove the observation. So the observation assumes that they're equal. So let's just put them.
Right, so we'll be within epsilon of each other.
So because they're equal and because these algorithms exist, for any epsilon, so for every epsilon, everything, the work we did shows this statement. For every epsilon, there exists some point in time, d epsilon, these are just the sequence of things returned by these algorithms such that this holds, okay? So now I want to define an algorithm C that computes this value, okay? So I'll define it orally. What algorithm C does is it takes as input, so it's good that we went over the definition of computability before. So algorithm C, which wants to compute the function, is given as input nk lambda and epsilon. And it runs A and B in parallel, and it just waits until this condition is satisfied. When it's satisfied, algorithm C returns the average of the two numbers, and that's it. And I claim that algorithm C is an algorithm that computes the function simply by the fact. The only thing we need to show is that it halts eventually. And the reason it halts eventually is because I know that this condition will be satisfied eventually, because I know that this converges to that and this also converges to that. Okay. Okay, so let me just end by telling you what is going to happen next. So next, I'm saying a few high-level words. So next, we're going to show the following theorem. So theorem, there exists a computable function. So it's important that it's computable, but it doesn't. The computable function, let's just call it, I don't know, f, that takes as input a Turing machine. So a Turing machine is just a description of an algorithm. So in particular, it's a valid input. Just imagine I'm given this algorithm, and it's going to read the algorithm, and it's going to return a triple NK lambda, such that if the Turing machine halts, it will always be the case that this is equal to 1, and if the Turing machine does not halt, it will always be the case that this is less than half. Okay, so in the language in computer science, this is a reduction. We're reducing the halting problem to the problem of optimizing these functions. Because this problem of deciding if a Turing machine halts or not is undecidable, it follows that this difference, there is no algorithm that is going to make this difference. In particular, the number is definitely not computable because we can't even tell if it's between 1 and a half. So we're going to show that. And I want to say maybe a little bit what we've gained. It seems like we've done something like quite strange, starting from a problem that was nicely posed, and it was about distinguishing different complex sets, and we end with a question in complexity theory. Okay. Okay, so one thing that we've achieved is that if you're coming at this from the mathematics side, studying quantum embedding problem or Kirchberg problem, this is all about the existence of very complicated algebras. The reason these problems are hard, presumably, is because we don't understand that much about the structure of infinite dimensional fundamental algebras, and it's hard to decide if there exist some of them that are not approximable in some sense in finite dimensions, or they're all approximable. Maybe we can't really figure that out. Here, by going through these steps, which are not our work, by the way, they're work of some of the others that I mentioned, we've completely done away with the infinite dimensional objects. This is, you notice that here, maybe I went a bit fast, but I made a choice. It would be enough to show that either omega star or omega infinity is uncomputable. That would wrap up the argument. I chose the easier one in a way. This is really a supremum of my function over finite dimensional sets. There's no infinite dimensional algebra. This is a completely finite dimensional problem, just any finite dimension. So this makes it much easier. I don't have to worry about okay. The second point I wanted to make is that I don't need to do that. I just like I said, I need to construct a specific linear function that distinguishes the two sets. And the question is, how do I do that? And the problem is that I don't know. This is what people in physics who study Bell inequalities do all the time. They try to find linear functions that separate the white set from the blue set. And this we have a few techniques how to do. But separating this from this, it seems extremely hard. So I'm kind of dodging, or we're kind of dodging, and saying, okay, instead we're going to not directly construct a function, but study this computability problem. And the main advantage that we gain, which I'll explain next time, is by formulating in this way, we gain like a very large class of functions lambda that we can construct. The lambdas that we construct, they're going to come, we're going to see them as things that are called nonlocal games or interactive proofs. And we're going to be able to use a lot of results that were developed in computer science for the design of interactive proofs. And these interactive proofs, they give us lambdas. And if we hadn't gone through this argument here, we wouldn't have had the idea of constructing these kinds of lambdas that come from this area. So it's kind of like connecting the two areas and then suddenly opening a large class of functions that we can play. In particular, I raised the title by now, but the third element in the title was MIP star equals RE. So I don't want to explain that because I'm out of time, but they're complexity classes. And RE is a complexity class that captures the same class of problems that's the halting problem. It's all problems that are no harder than the halting problem. This is RE. And problems that are no harder than distinguishing between these two, that's the class MIP. So this reduction shows the inclusion of RE in
at least say what acronyms stand for.
What, sorry?
What these MIP stand for?
It stands for multi-prover interactive proofs. I will get to say that a little bit, I think, next time. RE stands for recursively enumerable. So this is a set of all languages such that there's a Turing machine that spits out all elements of the language one by one. And the halting problem is complete for RE. So RE contains undecidable problems. Now, PSR is a little more complicated, but it's a class of all problems that can be decided in an interactive proof system. And I'll see you more next time. Okay, but now I'm much over time, so thanks.
Questions?
It was not clear from what you said if lambda will eventually be a construction that you can kind of write down what it is, or is it just an existence proof?
No, it wasn't. I mean, I didn't show, but it will be explicit in the sense that I won't be able to write it on the board, but in principle, I could print it out, all the coefficients. So N and K will be completely explicit. I won't actually get to full construction in that time, but.
So presumably it's useful in other situations.
Maybe. Maybe there's not so many examples, but maybe. I mean, for example, the main open question after this that some people in the audience are thinking about is whether you could use similar ideas to refute the hyperlinearity or sophisticity of conjectures. So now you're trying to construct groups. So this is the most directly related problem. Maybe you can also think about less directly related problems. Caleb?
So you made the definition of the blue region and the yellow region sound very analogous. So what is different about the definitions that allows you to get good outer approximations of the yellow region?
Yeah, that's a good question. Yeah, that's a good question. Yeah, I can prove it to you, but especially in the I raised the definitions, right? But why can't I get good outer approximations to the one, the blue one? I mean, I guess that's what the result shows, that we cannot do it, but it wasn't obvious at first. Otherwise, it had been done earlier. So yeah, I don't. In fact, really, I think this problem kind of, it's not clear which way you'd bet if you had to bet. So it might be that depending where you're coming from, you'd bet that they're equal, and in that case, you'd just think that the outer approximations for the yellow set are also valid for the blue set. I just have to prove it. So, not a good answer.
Okay, there does not seem to be any other questions, so thank you.